So the action potential is the electrical signal that the early researchers like Helmholtz discovered when they learned that they could create muscle contractions by providing like electrical stimulation. And we saw that that's exactly what happens in some cases with physical therapy, where part of the therapy might be stimulation that results in muscle contractions. What we are going to turn our attention to now is a different type of neural signal. This one was first studied by Lowy, who used studies of heart muscles. Basically, the heart is a muscle, and the heart has two nerves that go and stimulate it. One is the accelerator nerve, which you see here. That one speeds it up, it accelerates it. The other one is the vagus nerve, and the vagus nerve slows the heart. So we have like an accelerator and a brake, right, on the heart. And he would stimulate, say, the vagus nerve, and if you stimulate the vagus, okay, you should slow down the heart. If you do the opposite maybe and stimulate the accelerator nerve, then you should speed up the heart. And so he was doing that. But what he did on the second phase of the experiment was he took a solution from inside of the first heart, heart A, after it had been either sped up or slowed down through this electrical stimulation. He took this solution and injected it into the second heart. And lo and behold, he found that the second heart's rate of activity always changed according to whether it had been sped up by the accelerator nerve or slowed down by the vagus nerve in heart A. So just speeding up through electrical stimulation, heart A, and then injecting a solution from heart A into heart B is enough to change the rate of activity of this other heart, heart B, even though it had not been electrically stimulated. Therefore, Lowy concluded that there must be a chemical signal that controls heart activity as well, and neural activity, and that's what we're going to be looking at now. So when the action potential comes to the axon terminal, it is ready now to enter the second phase of neural communication, where we go to the synapse. And the synapse is a connection between a neuron and another cell. And so we'll be looking at a synapse between two neurons. The presynaptic neuron is the first one, neuron number 1, we can think of right here. And it's the one that's sending the signal. The postsynaptic cell we can think of as neuron number 2, and that's one that's going to receive that signal. And that signal that's going to travel through the synapse is going to be a chemical signal that we know of as a neurotransmitter. And we can think of as the synaptic cleft as just a term for the gap between the two neurons, the presynaptic and the postsynaptic neuron. For our purposes, if you just know synapse, presynaptic and postsynaptic, you're fine. So far, we've been talking about how a neuron can send a signal through the use of an action potential. So I'm just going to draw a neuron here. Here we go. And so we see the dendrites here. And we can see the nucleus, right? And the axon terminals, and then the myelin that wraps the axon and insulates it and allows the action potential, which is generated typically up here at the what's called the axon hillock, right in this area. That's usually where the action potential is generated. And then remember, the action potential jumps through what's called saltatory conduction from one node of RON-BA to the next. And every time that we get an action potential, remember it's the sodium entering during the rising phase, and then the potassium exiting during the repolarization when it goes back down with falling phase. So sodium in makes it go up, potassium out makes it go down. And what we're going to start looking at is what's going to happen here when the action potential gets to the axon terminals. And so let's bring another neuron in here. And this one also, of course, has dendrites and an axon and its own axon terminals. Because now, once the action potential gets to the end here of the axon terminal of neuron 1, it needs to, it's kind of, think of it like a relay race. It needs to pass that baton and get that message, relay that message to the next neuron in line. And then that next neuron in line is going to, generate its own action potentials and convey that signal forward to the next neuron. So on and on and on, right? And so this is the basis of information processing in our nervous systems. This is information being passed along, and in some cases we'll see that what happens is we get increases in neurotransmitters or decreases in neurotransmitters, or even in some cases the growth of new dendrites, or the removal of dendrites, or the addition of receptors, or the removal of receptors. So it allows for change and growth in our nervous system. So this basic relaying of information is key to everything that our nervous system is capable of. So now let's take a look at what happens at that synapse. So I'm going to zoom in a little bit here. And here we have the axon terminal of neuron number 1 forming a synapse with a dendrite of neuron number 2. And the action potential, remember, has just arrived. And we're going to see then what happens at this step in the process and how this action potential, when it arrives here at the axon terminal of neuron number 1, is going to set off a series of steps that's going to lead to the release of neurotransmitter that we see here. And so that neurotransmitter will get released onto the synapse, where it has a chance to bind to receptors on the dendrites of neuron number 2. Once that neurotransmitter binds to the receptors, then it might, for example, open up sodium ions, and then sodium might come in, and that could then trigger an action potential here in neuron number 2, and the signal is allowed to continue on through. So let's take a look at the steps involved in the release of neurotransmitter. The action potential depolarizes the presynaptic neuron, the presynaptic membrane. That makes calcium channels open, and calcium enters the axon terminal. So when the action potential arrives at the axon hillock, it triggers opening of calcium channels, and then calcium comes on in. The calcium leads the synaptic vesicles to fuse with the cell membrane there at the axon terminal and release their neurotransmitter, which is shown here in these little red dots, right? So the calcium comes in, the vesicles fuse with the membrane, and basically release the neurotransmitter into the synaptic space here, the synaptic cleft. The neurotransmitter then binds to receptors on the postsynaptic neuron, and we'll see that the receptor is specific to the type of neurotransmitter. We'll look at all the different neurotransmitters, and we'll see that there are often a variety of different receptors for every neurotransmitter. So a serotonin neurotransmitter might have 5 or 6 different receptors that it can bind to, and depending on the receptor it binds to, it can do different things. So it gives it flexibility. The next step is that an ionotropic receptor opens ion channels. We'll go over ionotropic and the other type, metabotropic, in a moment. But the most basic response is that the neurotransmitter binds to the receptor and it opens ion channels, changing the potential of the postsynaptic neuron. In other words, most likely it's going to open up sodium channels. That's going to make the neuron, the postsynaptic neuron, more positive, and that can then trigger what we're going to see is called an EPSP, an excitatory postsynaptic potential. Basically, it's going to provide a little bit of stimulation here, and if it's enough and it crosses the threshold required, then you might get an action potential here in the postsynaptic neuron. So let's take a look at these receptors. Ionotropic receptors cause ion channels to open, which immediately makes a neuron more or less positive. If it opens up sodium channels, sodium's positive, it's going to make the neuron more positive, and if it crosses that threshold from -70 to -60 millivolts, bam, you're going to get that action potential. It can also, though, open up ion channels that can make it more negative, and if it becomes more negative, then that's an example of inhibition. It's going to slow down neural activity in that pathway. So it can either lead to more action potentials or to fewer action potentials. The other type of receptor is more flexible and also more involved. It's a metabotropic receptor. It also opens ion channels, but it will have longer lasting effects because in addition to opening those ion channels, just like ionotropic receptors do, it can communicate with the neuron's DNA. And by doing this, it can make long-lasting changes. For example, it might make that postsynaptic neuron start producing more neurotransmitter or less neurotransmitter, or it might have it make more dendrites or get rid of some dendrites, or it might increase the number of receptors or decrease the number of receptors. So the metabotropic receptors is the one that allows our brain to really change, to have long-lasting changes. And we will see later on in the semester that the metabotropic receptor is the basis of memory.